is a place where we introduce intermolecular attractions. So intermolecular attractions, you'll often see me abbreviate them as IMAs or IMFs, so intermolecular attractions or forces. These are those sticky forces between molecules, not within a molecule, but between different molecules, that allows those molecules to stick or clump together in a sample. So when you have a glass of water, that's not one water molecule, but it's trillions and trillions of water molecules. And because of their IMAs or stickiness, they clump together to create that sample. So let's take a quick look here. So if we draw a water molecule, which you have known how to draw this for a long time, 1 oxygen, 2 hydrogens. And if we look at the molecule polarity, okay, so if we look at this across the x-axis, what we see above the plane does not match what we see below it, so it's asymmetrical. So water is an asymmetrical molecule because its bond distribution is not equal around the oxygen. It's a little bit lopsided. But then we also have to look at the END. So to describe the bonds, we have to look at the END. And hydrogen with an electronegativity of 2.2 and oxygen around 3.4 or 3.6, they're very different. The END here is greater than 0.5. So that means the electrons that are shared between this hydrogen and oxygen, they get pulled towards the oxygen, and we have a lopsidedness. So over here, what we see is the red in my diagram is the oxygen, and because oxygen pulls the electrons towards it and the bonds between it and the hydrogen, it carries a negative partial charge. So all the reds are oxygens, they carry a partial negative charge. Because the electrons are pulled away from the hydrogen in the bond, each of the hydrogens carries a partial positive charge. So I'm going to get that drawn in. So not only do we have a lopsided molecule, but we have partial charges that result from unequal sharing. It allows these attractions to occur. So think about things that you know about charges. So when you have like charges repel, right? So if you bring a positive charge near a positive charge, they don't pull together, they push apart. This one wants to go this way, and this one moves in the opposite direction. Same thing if you have 2 negative charges, they want to push away from each other, so they repel. But opposite charges attract. So when you have something that is positively charged and something else that's negatively charged, instead of repelling, they pull towards each other in an attraction. So what happens in a huge sample, like where it contains trillions of water molecules, is that the partial negative side of the water, which is where the oxygen is, the oxygen in one water molecule is going to be attracted to the hydrogen side of a different water molecule because they have opposite partial charges. And this just occurs. So the molecules align themselves based on differences in their partial charges. And so when these molecules align themselves, like this orange dotted line, this is an IMA. Intermolecular attractions are much weaker than the individual bond. So what's here, this is the covalent bond that is within the molecule versus the attractions that is between different molecules. So covalent bond polarity. So as that polarity increases, okay? That means that we have a larger END, so we have more definite partial charges. Molecule polarity, as it increases, we see a greater degree of asymmetrical or asymmetry in the shape. So asymmetrical shape becomes more asymmetrical. That should be the word larger. So now there are different types or rankings of intermolecular attraction. So we're just going to try to keep it simple. So if two different molecular compounds are both nonpolar, okay, the substance with the higher or larger GFM will have the stronger IMAs. And so here the thing is, the stronger the IMAs, the higher the boiling point, the higher the melting point, the lower the vapor pressure, meaning it takes more heat energy to force a phase change for the molecules to separate, to go from a solid to a liquid to a gas. So when we are forcing a molecule to go from a liquid to gas or solid to a liquid, what we're doing is we're weakening these IMAs. Covalent bonds stay intact. These are what are, their strength is changed. So this is what we are talking about, is that attraction between these molecules. So take a look here. You may be asked to predict which substance or explain why one substance has a higher or lower boiling point in reference to the intermolecular attractions. So take a look. Ki. Ki has a metal and a nonmetal, so it's ionic in nature. Hi is a nonmetal with another nonmetal, so it's a covalent bond, meaning it's a molecule. Ki will have the higher BP because it's ionic. Now, taking a look here. Second examples, we have F2 versus Cl2. These are both molecules. So it's a molecule and a molecule. And when you draw it out, you have a diatomic, F bonded to an F, so it's nonpolar. You have a Cl bonded to a Cl, it's also nonpolar. So it's not as easy to tell apart. So we have both nonpolar molecules. So the one that we choose is we choose Cl2 will have the higher boiling point because it has the greater GFM. Okay, last example, you have nonmetal bonded to nonmetal. So this is a molecule linked with covalent bonds. Carbon and Cl are both nonmetals, so it's also a molecule. But when you draw it out, okay, we have a pyramidal versus a tetrahedral shape. So this one is a polar molecule because it's asymmetrical, and this one has symmetry, so it's a nonpolar molecule. So NH3 we would choose to, or predict to have the higher boiling point because it is a polar molecule. It has that asymmetry. Keep it simple. If